I'm going to start with an example that many of you have heard of. It's Hilbert's Hotel, and it's meant to bring out one of the weird features of infinities. So suppose that we have a hotel, which, unlike normal hotels, has infinitely many rooms. So it has room 0, and room 1, and room 2, and room 3, and so forth, one for each natural number. And let's assume that it's completely full. So each room has someone inside it. And to make things simple, let's also number the people in our rooms with natural numbers. So that's 0, and that's 1, and that's 2, and that's 3, and that's 4, and so forth. So in a finite hotel, if you have someone in every room, then that's it. The hotel is full, and there is no way of bringing an additional person into your hotel without some kind of room sharing. The weird feature of infinite hotels, and in a way that will be like key to everything we're going to be doing over the next 3 weeks, is that when it comes to infinite hotels, you can fit an additional person in. And the way to do it is just have the hotel manager make an announcement and say, OK, could everyone please move one room to the right? That means that person 0 moves to room 1, so now 0 isn't there, and person 1 moves to room 2, so 1 isn't there, and so forth. So we now get 2 results. So the first is that room 0 is empty because its resident moved out and nobody moved in. But then, and this is the really remarkable thing, everybody got a room because for person n, room n plus 1 was available because it was vacated by person n plus 1, who now lives in room n plus 2. Now, here's a question for you guys. Does this require an infinite room? So it's true that there are infinitely many rooms, and it's true that for each natural number n, there's an nth room. But does this require that there be like some room which is infinitely far away from the first room? Yes?
Do you define that as like countably infinite? So the fact that, like, a way of putting it, so there's someone at room 0, and there'll be someone at room 10 billion, and that'll keep going on, so you can count all the way. Because then, in that case, it would be yes. Because in the original problem, you mapped n to n. Now you're mapping n to n plus 1 rooms to people. So then, in that case, there would always be an infinite way amount far away, I guess.
Oh, no, good. This is very interesting. This is very interesting. So I'm glad you talked about countable infinity because that is what we're going to talk about today. So here's something that happens. It's certainly true that each room has a number, and the number for each room is a natural number, in other words, a finite number. There's no bound to how big those numbers can get. So for any k, some room is going to have a number bigger than k. But no room has a number which is itself infinite. Now, if you ask how many rooms are there, it's going to turn out that the answer is countably infinite many rooms. And we're going to be more precise about what that means. But crucially, there is no room which has an infinite number, and no room which is infinitely far away from room 0. And now notice the following. Suppose that instead of having one person try to join the already full hotel. This time we had like 5 billion people try to join it. It would be just as easy to accommodate them. All we need to do is ask each person to move 5 billion rooms to the right. And that will liberate 5 billion rooms so we can accommodate our new guests. I mean, it's really remarkable. As it turns out, it's even possible to accommodate infinitely many new guests. So can anyone think about how to do that? Okay, so you've spoken, so how about you?
You can just tell every original guest to move to twice their current room number, and that will leave gaps at every odd number where you can fit the infinitely many new guests.
That's right. That's right. So, I mean, under this new distribution, what happens is that, okay, so imagine we start with our original full hotel. And then what happens is that, as you said, each person looks at the room number. And if the room number is n, they go to room 2n. So 0 stays because 2 times 0 is 0. So person 0 is in there. Person 1 moves because 1 times 2 is 2. So person 1 moves to room 2. Person in 2 is going to move to 4 because 2 plus 2 equals 4. The person in 3 is going to move to 6. The person in 5 is going to move to 10, and so forth. So generally speaking, each person is going to end up having a number which is the room number divided by 2. And then, as you pointed out, every odd-numbered room is free. And we can just say to our new guests, OK, if you're a new guest and your number is n, please move into room 2n plus 1. So here's what we're going to say. That is a crucial definition. So we want to say that the number of elements in A, so these two little bars, refer to the cardinality of the set. The number of things in A is less than or equal to the number of elements in B, which I will sometimes read, there are at least as many things in B as there are in A. That, by definition, means that there is a 1-1 correspondence from A into B. So just so everyone is clear about the notation, so a 1-1 function is just a function that never maps distinct elements into the same thing. So our 1-1 function never takes two elements of A and maps them onto the same element of B. But because we allow our 1-1 function to go from A into B as opposed to from A onto B, then what that means is that there can be things in B to which nothing was assigned. There's a theorem which is important, but I'm not going to prove, which is this. It shows that if the cardinality of A is less than or equal to the cardinality of B, and vice versa, then A and B have the same cardinality. Where I should add where the cardinality of A equals the cardinality of B, it just means that there's a 1-1 correspondence from A onto B. OK, so that's our basic machinery. So basically we're done in terms of definitions, like for the whole 3 weeks. So we're going to talk about some cool examples, but before we do, is everybody clear about just what the basic definitions are? We can always come back to it. Okay. All right, so here is a first fun question for you guys. So take the natural numbers first, and then take the rational numbers. So the rational numbers is the set of numbers of the form AB, where A and B are natural numbers, and B is not 0. So the first question, and this is what really, this result is what like gave rise to the field. Is it the case that there are just as many as one of the other, or not? Or are there more rational numbers than real numbers? I mean, we know that there are going to be at least as many rational numbers as natural numbers, because every natural number is a rational number. So it's very easy to define a function from the natural numbers, a one-one function from the natural numbers into the rational numbers, just the identity function. The difficult question is the other way around. Is it possible to find a one-one function from the rational numbers into the natural numbers? And as it turns out, the answer is yes. And if this doesn't blow your mind, I do not know what will. So here's a proof. So start by drawing a grid, which is infinite, both going to the right and going down. And write down every rational number in some cell of that grid. So we can just write 0, 1, 0 over 2, 0 over 3, 0 over 4, and so forth. And then 1 over 1, and 1 over 2, and 1 over 3, and so forth. And we just keep going. Okay. And now can anyone think of a way of assigning yes? Oh, precisely, precisely. Yes, she gave her answer with a hand gesture, so I will interpret. So here's what you can do. So every single rational number is on this grid, every single one. So if we're to show that you can assign each rational number to some natural number, then we will have succeeded in showing that the rational numbers are their number is smaller or equal to the number of the natural numbers. And because we know that the converse is true, we will have shown that there are just as many as one as there are of the other. And here's how to do that. So we're going to travel a diagonal path. So we're first going to visit this guy, and then these guys, and then these guys, and we keep going. And in walking our path, we're going to assign each new rational number we encounter a natural number. So to this guy, we're going to assign 0. And then to this guy, oh, we would have assigned 1, but that guy is 0 already, so we're actually going to eliminate that square. Next one I visit is this one. To that one, we're going to assign 2. And then, OK, that's 0 again, so we're going to ignore it. And this is 1/2. To this one, we assign 2. To this one, 3. That one's 0 again. To this one, we assign 4. That one's 1, so we'll eliminate that one. That one, we assign 4. And we keep going. So that means that every rational number got assigned a different natural number. So in our sense of just as many as, there are just as many rational numbers as there are natural numbers. Yes?
You could also do the second column and then down and left in the second row, and the third column and down into the left
Yeah,
row.
that's a nice technique. Yeah, so let's do it that way. This is getting kind of crowded, so I'm just going to erase it and start again. So we have our grid. I won't write down the rational numbers again. So is this the technique you mean? So you first do this, and then you do that, and then you do this, and then you do that, and then you do this, and then this, and then that, and then that, and then that, and then that, and so forth? Oh, there's even another one.
No, I was thinking, can I just
Yes,
draw it?
sure. In fact, I'll prepare the grid for you. Yeah? Oh, that's right. So like you make squares. Oh, yeah, I love it. I love it. In fact, I think this is my new favorite technique. That's right. Notice, by the way, that this shows that if you have your hotel, and it's not just that you get infinitely many new guests, but you get infinitely many groups, each of which consists of infinitely many new guests. You can fit them into the hotel. Because look, think of each column in this infinite grid as corresponding to one group. So this is your group 1, and your group 2, and your group 3, and group 4, and so forth. And then these are the members of each group. So this is 0 in the first group, 2, 3, 0 in the second group, 1, 2, 3, and so forth. And then what you can do is you can use this technique to assign a natural number to each of these guys in such a way that different people get assigned different numbers. And then you can just use the technique we already knew about. So you have your totally full hotel, and you say, OK, if you're in room N, move to room 2N. That will liberate infinitely many rooms. And then you look at these guys and say, OK, we assigned a natural number to each of you guys. Just look at your number and move to room 2 times that number plus 1. And he's like, that is. OK, so at that point, I knew I wanted to be a philosopher. Even though there is a result which is even more remarkable than that one. OK, because one thing that it's tempting to think at this point is that all infinite sets are the same size. So like if sets so different as the rational numbers and the natural numbers turn out to be the same size, you think, well, like once we move to infinity, like basically any infinity is the size of any other infinity. But it turns out that that is not correct. OK, so the next thing we're going to prove is that there are more real numbers than natural numbers. And because the natural numbers and the rational numbers are in fact of the same size, it follows from that result that there are also more real numbers than rational numbers. Okay. So there's so many real numbers that I actually don't even need to look at all of them. So all I'm going to do is I'm going to look at the real numbers in that interval. So the real numbers bigger or equal to 0, but smaller or equal to 1. And what I'm going to show is that even in there, even in that small interval, there are more points than there are natural numbers. And the way I'm going to do it is I'm going to proceed by reductio. So I'm going to assume the opposite of what I want to prove. And I'm going to show that you can prove a contradiction from that assumption. So if that assumption leads to a contradiction, it can't be right. So the opposite of what I want to prove can't be right. So what I want to prove has got to be correct. So this is what I'm going to assume for reductio. I'm going to assume that there is a 1, 1 function from the real numbers in 0, 1 into the natural numbers. So notice, if that were true, then we would know that the cardinality of that guy is smaller or equal to the cardinality of the natural numbers. But we also, we trivially know this. We know trivially that the cardinality of the natural numbers is smaller or equal to the cardinality of these guys. So can anyone think of a quick proof of this? So in other words, a 1, 1 function that takes us from each natural number to a number in there? Yes?
Just the function 1 over that natural number.
Correct. So I'll do that over here. So function that assigns, well, it's not going to work for 0, but I'll correct that later. So it assigns to 1, 1 over 1, and assigns to 2, 1 over 2, and to 3, 1 over 3. And of course, all these guys live comfortably in there. And what about 0? Well, we can just assign it whatever other element of there we want, provided it wasn't already taken. So for example, pi minus 3. So that means that we know for sure that the natural numbers are equal to or less than the real numbers in there. So if we could show this, that would mean that there are exactly as many real numbers in that interval as natural numbers. What I'm going to do is I'm just going to assume this to see what happens. I'm going to derive a contradiction from the assumption. And if I'm able to derive a contradiction, the assumption can't have been correct. So this must have been false. Okay. we're assuming that there is a 1, 1 function from the real numbers into n. So let's just write out what the beginning of that function looks like. So what it means is that a bunch of natural numbers got assigned real numbers. So maybe 0 got assigned that one, 2 got assigned, 1 got assigned that one. Maybe 2 didn't get assigned anyone. That's fine. 3 got assigned that guy, and so forth. So we have a long list. And crucially, our list leaves no real number out. So every real number in our interval is in this list at some point. So that's what we're assuming. What we're assuming is that we can, in effect, list the real numbers in 0, 1. Yes?
Sorry, I think I just missed something. What's that x there?
Oh, the x. So our assumption is that there is a 1, 1 function from the interval into n. So that means that to each member of our interval, we assigned some natural number, that no 2 real numbers in our interval got assigned to the same natural number, but we're not assuming that there weren't any natural numbers left over.
Yeah.
We're assuming that this is a function into the natural numbers, but not onto the natural numbers.
Oh, I get that. I just think I just missed something as far as what that x means, where like it's R0, R1, and then R3. Like.
Oh, it just means that I didn't assign anything to 2.
Oh, x. Oh, yeah, I see. Yeah.
Sorry about that.
Yeah.
Sorry about that. In fact, this makes things yucky. So what I'm going to do is, if you have a listing with spaces, it's very easy to turn it into a listing with no spaces. All you need to do is, whenever you find a space, move things up.
Yeah.
OK, so what I'm going to assume with no loss of generality is that our listing has no spaces. So I'm going to assume that each natural number got assigned some real number, and crucially, that no real number in the interval was left out. That's going to be essential. So we have our list, and no r in the interval is left out. OK, and now we're going to prove our contradiction. So the first observation en route to our contradiction is that the real numbers in 0, 1 can all be written out using decimal expansion. So we can write each of them out as something of the form 0.A1, A2, A3, blah, 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 where each of these is just a digit between 0 and 9. So I'm going to do it for each of them. I'll write one more. OK. So we have our list. And everyone in the interval is somewhere on that list. So now consider the diagonal number. So take the first digit from the first member in our list, and the second digit from the next member on our list, and the third digit from the next member on our list, and a fourth digit in the next member of the list, and so forth. And look at that real number. So we have our diagonal number. That's 0.A1, B2, C3, D4, E5, and so forth. That's just a real number in the interval. And it has an evil twin. So to construct the evil twin, use the following recipe. Say that where D has 2, write, for example, 7. And where D has no 2, write 2. That's how you construct the evil twin. So suppose, for example, I don't want to erase this. I'll continue over here. So suppose, for example, that our D is this number. Then D's evil twin is going to be 0 point, and then we found something which is not a 2, so we write a 2, and then something is not a 2, so we write a 2, and then we find a 2, so we write a 7. And then something is not a 2, so we write a 2, and then 7, 2, 2, 7, 7, 2, and we keep going. And now we're done. Because D's evil twin cannot be on our list. Why is it not on the list? Well, look, it can't be the first member on the list because this number differs from the first number on the list in at least its first digit. And it can't be the second member of the list because this number differs from the second member of the list in at least its second digit, and so forth. So here's what we've done. We found a number, and this number has got to be in the interval 0, 1, which is not on our list. But we had assumed that every real number in the interval was on our list. So we've proved, contrary to our assumption, that that cannot be correct. So we've proved a contradiction. So if our assumption for reductio entails a contradiction, our assumption for reductio cannot be correct. So we have shown that the real numbers in 0, 1 are not smaller in number than the natural numbers. Most people see this proof the first time and don't understand it. So what I'm going to do is I'm going to sit down and make sure that people don't have questions, because I bet some people do have questions. So possible questions are, I don't understand proof by reductio. I don't get why you keep saying that all real numbers in the interval should be on the list. Could be, I don't get how you constructed D. It could be, I don't get, yes!
I don't get how you constructed D.
Ah, good, good. Thank you for asking. Okay, so we were assuming by reductio that you can basically assign each real number in our interval into some natural. So we can use that assumption to list our real numbers. So, let that guy be whatever was assigned to 0, that guy whatever was assigned to 1, and so forth. And then we just know that every real number in our interval has some decimal expansion. So write it out using its decimal expansion. Once you've written them all out, you can focus on particular digits. So you can say, okay, just tell me what the first digit in the decimal expansion of the number you assign to 0 is. Whatever it is, write it down there. And then ask what is the second digit in the decimal expansion of the number you assign to 1 is. And whatever it is, write it there. And you keep going with the third and the fourth and the fifth and the sixth. And then you get this number, which is just a real number. It's the one that you got from diagonalizing the elements in the list. And that number is not quite trouble. So that number could be on the list. So in fact, maybe it's this number. It'll be this number if it turns out that A2 equals B2, and A3 equals C3, and A4 equals D4, and so forth. But its evil twin cannot be. Is that better? Now, there's a little thing that I skipped, which is the fact that some numbers, some real numbers in our interval, have more than one decimal notation. Can anyone give me an example of a number in there with more than one notation? Yes.
Do you mean ending with an infinite series of zeros or nines?
Yes. Okay, so for example, one half, which is in there, can be written out like this, but it can also be written out like that. The way to know that those are actually the same number is that if they were different numbers, then the difference between them would have to be some real number. But the real number has to be smaller than 1 over 100, and smaller than 1 over 1,000, and smaller than 1 over 10,000, and so forth. And there is no real number greater than 0, which satisfies all those conditions. So the difference between these two guys has to be 0. So they are the same number. So one tricky issue which I ignored in my proof is that you can say, okay, well, it's true that the evil twin cannot be on this list in the sense that that exact notation can't be on the list. But what if you had that same number written out using some different notation? So what's the answer to that challenge? Yes?
Instead of using 0 through 9, just use zeros and ones.
You mean zeros and ones to, you do it in binary?
Non-binary, just restrict it to a subset of zeros and ones, the infinite sequences.
Oh, I see. I see what you're saying. Okay, so let me make sure I've understood. So you say, look, in order to prove this result, you don't need to look at all real numbers in that interval. It's enough to show that if you look at only some, you can't produce a list. And just pick them carefully so that you never get this problem. I think that's right. I think that works. Now, here's another thing that would work too. So even though it's true that some real numbers can be written out in more than one way using decimal notation, the only case in which you can get that is where you have one rotation which ends with an infinite sequence of zeros and a corresponding one which ends with an infinite sequence of nines. And in choosing my recipe for generating evil twins, I was careful to do so in a way that involved neither zeros nor nines. So the evil twin is guaranteed to be someone who has a single notation. So it can never happen that this guy is written out on this list with that notation or with any other notation, because there's only one notation. Okay. So this is what we have so far. So what we have is that infinity can be tamed. The way to tame it is by using the notion of 1-1 correspondence to talk about whether different infinite sets are the same size or one is bigger than the rest. And we've proved two basic results. The first is that there are just as many natural numbers as there are rational numbers. The second is that there are more real numbers than there are either of the two previous sets. So there are more real numbers than natural numbers and more real numbers than rational numbers. What we're going to do next time is show that for any infinite set, there's a bigger one. So we have infinitely many sizes of infinity. And like things get really weird. Okay, see you Wednesday.